Hello there, and welcome to Whispers of Science, where the universe's most puzzling secrets get the gentle treatment they deserve. Tonight, we're settling into one of the most beautifully baffling phenomena in all of physics: quantum entanglement, a mystery so profound that even Einstein himself called it spooky action at a distance. And if that doesn't make you curious, well, perhaps you're already asleep, which is perfectly fine by me. Before we drift into this quantum wonderland, I'd love to know where in the world you're listening from tonight and what time it is in your corner of the cosmos. It's rather fitting, isn't it? A video about particles mysteriously connected across vast distances. And here we are, scattered across time zones, yet somehow sharing this very moment together in the soft glow of our screens. If you find this gentle journey through the quantum realm soothing or perhaps just wonderfully bewildering, I'd be ever so grateful if you tapped that like button and maybe subscribed it. Helps this quiet corner of scientific wonder reach other curious souls who might need a peaceful pause from the ordinary world. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll drift off, having learned something extraordinary about the very fabric of reality itself. So settle in, slow your breathing, and let's begin. Because somewhere between the impossibly small and the utterly incomprehensible lies one of nature's most elegant mysteries. Quantum entanglement sounds like something from a science fiction novel, doesn't it? Two particles, separated by vast distances, somehow knowing instantly what the other is doing, communicating faster than light itself, defying everything our everyday experience, tells us about how the world should work. And yet, this spooky phenomenon isn't fiction. It's one of the most thoroughly tested and verified aspects of quantum mechanics. Imagine, if you will, two coins, not ordinary coins, but magical ones with a very peculiar property. When you flip one and it lands heads the other, no matter how far away, will instantly land tails every single time, without fail, without delay, without any signal passing between them. This seems impossible. Surely there must be some hidden communication, some secret message racing between the coins, but quantum entanglement suggests otherwise. The mystery begins in the early 20th century when physicists first started peering into the atomic world. What they found there challenged every assumption about reality itself. Particles didn't behave like tiny billiard balls rolling around predictably. Instead, they existed in strange states of possibility, neither here nor there, neither spinning up nor spinning down, until the moment someone looked at them. It was as if reality itself was fundamentally uncertain, waiting for observation to collapse the wave of possibilities into a single concrete outcome. This was disturbing enough. But then came an even stranger realization. These quantum particles could become entangled, their fates mysteriously intertwined in ways that seemed to mock the very notion of locality. The idea that objects are only influenced by their immediate surroundings. Einstein, along with his colleagues Podolsky and Rosen, couldn't accept this. They published a famous paper in 1935 arguing that quantum mechanics must be incomplete. There had to be hidden variables, they claimed, secret properties that predetermined how particles would behave when measured. Surely nature wasn't actually uncertain. Surely particles didn't communicate instantaneously across the universe. But nature, as we've learned, has a sense of humor, and it doesn't much care what makes us comfortable. Decades of experiments have confirmed that quantum entanglement is real. Particles can indeed become correlated in ways that seem to violate our everyday understanding of space and time. When you measure one entangled particle and find it spinning up, its partner will always be found spinning down, no matter how far apart they are, no matter how quickly you measure them. This isn't because they were predetermined to be opposite. It's because they exist in a superposition of all possible states until measurement forces them to choose, and when one chooses the other, instantly knows what choice to make, even if they're on opposite sides of the galaxy. It's as if the universe has a cosmic telephone network operating at infinite speed. Now you might be thinking this sounds like the perfect way to send messages faster than light if changing one particle instantly affects another. Surely we could use this for communication, but here's where quantum mechanics reveals another layer of its beautiful strangeness. While the particles are indeed connected, you can't control what you'll measure when you observe your particle. You get a random result, up or down, heads or tails, completely unpredictable. The person measuring the other particle will also get a random result, but here's the magic when they compare their results. Later, they'll find perfect correlation. Every time you got up, they got down. Every time you got heads, they got tails. But neither of you could predict or control what you'd measure. The correlation only becomes apparent when you compare notes afterward. This means you can't use entanglement to send information faster than light, because the information only exists in the correlation between random results. It's like having two magic 8 balls that always give opposite answers, but you can't shake yours to make the other one say what you want. The connection is real, but it can't be exploited for communication. The implications of this are staggering. It suggests that our usual notion of separate objects existing independently in space might be an illusion at the quantum level. Particles that have interacted remain connected in some fundamental way, regardless of the distance between them. The universe, at its deepest level, might be far more interconnected than our everyday experience suggests. Think about it for a moment. Every particle that makes up your body was once part of something else, a star perhaps, or a primordial cloud of gas. These particles have interacted with countless others throughout cosmic history, creating a vast web of quantum correlations that spans the universe. In a very real sense, you are quantum entangled with the cosmos itself. But let's not get too carried away with the mystical implications. Quantum entanglement, while mysterious, is also incredibly practical. It's the foundation of emerging technologies like quantum computing and quantum cryptography systems that could revolutionize how we process information and secure our communications. The same spooky action that baffled Einstein might one day power computers capable of solving problems that would take classical computers longer than the age of the universe. The journey to understanding entanglement has been filled with brilliant minds, grappling with concepts that seem to defy common sense, from Einstein's skeptical genius to John Bell's groundbreaking theorem to Alan Aspect's elegant experiments that finally put the matter to rest. Each step has revealed new layers of strangeness in the quantum world. Bell's contribution deserves special mention. He devised a way to test whether Einstein's hidden variables could exist or whether quantum mechanics truly described reality. His theorem showed that any theory based on local, hidden variables would produce correlations weaker than those predicted by quantum mechanics. When experiments were finally performed, they confirmed quantum mechanics and ruled out local hidden variables. The universe really is as strange as quantum theory suggests, but perhaps the most beautiful aspect of quantum entanglement is what it tells us about the nature of reality itself. It suggests that the boundaries we perceive between objects might be somewhat arbitrary, that connection and correlation might be more fundamental than separation and independence. This doesn't mean everything is connected in some New Age mystical sense, but it does mean that the universe is far more subtle and interconnected than our intuitions suggest. As we drift deeper into this quantum mystery, we'll explore how entanglement actually works at the level of individual particles. We'll meet Schrodinger's famous cat of thought experiment that illustrates the bizarre implications of quantum superposition, and we'll discover how modern experiments have turned Einstein's philosophical objections into practical technologies that might reshape our world. We'll also delve into the question of what entanglement really means for our understanding of space and time. Does information really travel faster than light between entangled particles? Or is something more subtle happening? Are particles communicating across the void, or are they never truly separate? To begin with, these questions have puzzled physicists for decades, and the answers might surprise you. The story of quantum entanglement is still being written. New experiments push the boundaries of what's possible, creating entangled states with more particles over greater distances. For longer periods of time, scientists have entangled photons across continents, created networks of entangled atoms, and even achieved entanglement between fundamentally different types of particles. Each advance brings us closer to practical quantum technologies while deepening our appreciation for the mystery. So, as we prepare to dive deeper into this quantum rabbit hole, remember that we're exploring one of the most profound mysteries in all of science, a phenomenon that challenges our most basic assumptions about reality while opening doors to technologies that seemed impossible just decades ago. Whether you're here for the science, the philosophy, or simply the wonder of it all, you're in for quite a journey in our next segment. We'll examine exactly how particles become entangled in the first place and why this process seems to create connections that transcend space and time. We'll explore the mathematics behind the mystery without getting lost in equations and discover why quantum entanglement might be the key to understanding consciousness computation and the very nature of existence itself. For now, though, let yourself marvel at the simple fact that the universe is far stranger and more wonderful than our everyday experience suggests two particles dancing together across the cosmos, connected by invisible threads of correlation, defying distance and time in their eternal quantum waltz. It's enough to make anyone believe in magic, even if that magic happens to be called physics. To truly understand quantum entanglement, we need to journey back to the very beginning to see how these mysterious connections first form. Picture two photons, particles of light, born together in a single quantum event, perhaps created when a laser beam passes through a special crystal, or when an excited atom releases its energy in a burst of illumination. These twin particles emerge into the world already sharing a profound bond, one that will persist no matter how far they travel. When these photons are created, they don't emerge with predetermined properties. Instead, they exist in what physicists call a superposition, a ghostly state where both particles simultaneously possess all possible characteristics. They are neither vertically nor horizontally polarized, neither spinning clockwise nor counterclockwise. They are everything and nothing all at once existing in a realm of pure possibility. This superposition isn't just a limitation of our knowledge. It's not that the particles have definite properties that we simply don't know about. Rather, the particles genuinely exist in multiple states simultaneously until the moment we choose to measure them. It's as if nature itself is undecided, keeping all options open until forced to make a choice. Imagine, if you will, a cosmic dance where two partners move in perfect harmony without ever practicing together, without any choreographer to guide them. When one twirls left, the other spins right. When one leaps high, the other dips low. Their movements are perfectly correlated, yet completely spontaneous. This is the essence of quantum entanglement, a correlation without communication, a connection without cause. The moment you decide to measure one of these entangled particles, something remarkable happens. The act of observation forces it to collapse from its superposition of all possibilities into a single, definite state. But here's where the mystery deepens. The instant your particle chooses its state, its distant partner somehow knows to choose the opposite state, not because any signal has passed between them, but because they remain fundamentally connected at the quantum level. This connection transcends our everyday understanding of space and time. The entangled particles don't send messages to each other. They don't communicate through any known force or field. Instead, they seem to share a single quantum state distributed across space, like two pages of the same book that always tell the same story. No matter how far apart the pages might be, the mathematics that describes this phenomenon is elegantly simple yet profoundly strange. The combined quantum state of both particles can be written as a single equation that cannot be separated into independent parts for each particle. This mathematical inseparability reflects a physical reality that two entangled particles are not really two separate objects, but rather two aspects of a single quantum system. Scientists have spent decades trying to understand how this connection actually works. Some have proposed that information does indeed travel between the particles faster than light, creating what physicists call nonlocal correlations. Others suggest that the connection never really breaks, that entangled particles remain part of a single quantum object, regardless of the distance between them. Still others have speculated that our understanding of space and time itself might be incomplete, that the universe might be fundamentally different from our everyday experience suggests. In this view, entanglement doesn't violate the speed of light because the particles were never truly separate. To begin with, they exist in a realm beyond our ordinary concepts of here and there, now and then. The experimental verification of quantum entanglement reads like a detective story filled with ingenious tests and surprising revelations. In the 1970s, physicist John Clauser performed the first decisive experiments using entangled photons to test Bell's theorem. His results confirmed that quantum mechanics was correct and that local hidden variable theories could not explain the observed correlations. But Clauser's experiments still left some room for doubt. Perhaps the detectors were somehow coordinating their responses, or maybe the particles were communicating through some unknown mechanism. To close these loopholes, physicists devised ever more sophisticated tests, each one designed to eliminate alternative explanations for the mysterious correlations. Alain Aspect in France conducted groundbreaking experiments in the 1980s that closed the most significant loophole by switching the measurement settings while the photons were already in flight, ensuring that no signal could coordinate the particle's behavior. His results were unambiguous. Quantum entanglement was real and local realism. The idea that particles have definite properties, independent of observation, was false. More recent experiments have pushed the boundaries even further. Scientists have created entangled states between particles, separated by hundreds of kilometers, using satellites to distribute quantum correlations across continents. They've entangled not just pairs of particles, but entire networks, creating quantum webs that span vast distances. These advances aren't just academic curiosities, they're laying the groundwork for revolutionary technologies. Quantum computers rely on entanglement to perform calculations that would be impossible for classical machines. By manipulating entangled quantum bits or qubits, these devices can explore multiple solutions simultaneously, potentially solving problems in cryptography, chemistry, and physics that currently seem intractable. Quantum cryptography uses entanglement to create communication channels that are fundamentally secure. Any attempt to eavesdrop on an entangled quantum message necessarily disturbs the quantum state, alerting the communicators to the presence of an intruder. It's like having a conversation where any attempt to listen in automatically changes what's being said. Perhaps most intriguingly, quantum entanglement might help us understand consciousness itself. Some scientists have speculated that the brain's ability to maintain coherent thoughts and experiences across billions of neurons might rely on quantum effects, including entanglement. While this remains highly speculative, it suggests that the spooky connections between particles might play a role in the mystery of awareness itself. The philosophical implications of entanglement continue to puzzle scientists and philosophers alike. If particles can be correlated without communication, what does this tell us about the nature of reality itself? Does it mean that everything in the universe is ultimately connected, or that our concepts of separate objects are fundamentally flawed? Some interpretations of quantum mechanics suggest that entanglement reveals the universe to be a single interconnected whole, where the boundaries between objects are merely convenient fictions. In this view, individual particles are like waves on an ocean, appearing separate but ultimately part of a single underlying reality. Others maintain that entanglement is simply a feature of quantum systems, without broader implications for the nature of reality. They argue that the correlations between entangled particles are real, but don't necessarily mean that everything is connected. In some mystical sense, the universe might be stranger than we imagine without being magical. As we explore these questions, it's worth remembering that quantum entanglement isn't just a theoretical curiosity, it's a practical reality that scientists work with every day in laboratories around the world. Researchers routinely create entangled states, manipulate quantum correlations, and use these effects to perform tasks that would be impossible with classical physics. The technology is advancing rapidly. What once required room-sized equipment can now be achieved with devices that fit on a tabletop quantum sensors that rely on entanglement, can measure magnetic fields with unprecedented precision. Quantum networks that distribute entangled particles are being tested in cities around the world. Yet, for all our technical mastery, the fundamental mystery remains: why does nature allow particles to be connected in this way? What purpose does entanglement serve in the grand scheme of the universe? These questions don't have easy answers, but they remind us that even our most advanced scientific theories leave room for wonder. Perhaps that's the most beautiful aspect of quantum entanglement. It shows us that the universe is far more subtle and mysterious than our everyday experience suggests. Reality operates according to rules that seem impossible yet work perfectly, creating a world where particles dance together across cosmic distances, where information and correlation transcend space and time. As we continue our gentle journey through this quantum landscape, we'll discover how entanglement challenges our most basic assumptions about causality, locality, and the nature of information itself. We'll explore the strange world of quantum superposition, where particles exist in multiple states simultaneously, and we'll meet some of the brilliant minds who've dedicated their lives to understanding these mysteries. But for now, let yourself drift with the wonder of it all somewhere in the universe. Right now, particles that were born together billions of years ago are still connected, still dancing their mysterious quantum dance, still proving that reality is far more beautiful and strange than we ever dared imagine. In the heart of a laboratory in Vienna, a single photon splits into two, creating what scientists call an entangled pair. One photon travels north toward Innsbruck, while its twin journeys south toward Geneva. These particles of light, racing away from each other at incredible speed, remain mysteriously connected in ways that would make even the most imaginative storyteller pause in wonder. When the northern photon encounters a detector and reveals itself to be spinning clockwise, its southern twin instantaneously becomes counterclockwise, not because any message has passed between them, but because they share something far more profound than communication. They share existence itself in a realm where distance becomes meaningless and time loses its grip on cause and effect. This is where quantum entanglement reveals its most beautiful paradox. The faster these particles separate, the more dramatically they demonstrate their connection. It's as if the universe has written a love story where separation only strengthens the bond, where distance becomes irrelevant to devotion, and where the act of looking at one instantly affects the other, regardless of the cosmic gulf between them. But how do we actually observe this mysterious connection in practice? The process is surprisingly elegant, yet technically demanding. Scientists use devices called polarizers, which act like quantum coin flippers. When a photon encounters a polarizer, it must choose a direction to oscillate, either up and down or left and right. The choice appears random, like a fair coin toss with equal probability of either outcome. Here's where the magic reveals itself. While each individual measurement seems completely random, when scientists compare the results from both entangled photons, they discover perfect correlations. If the northern photon chooses up, the southern photon always chooses down. If one goes left, the other invariably goes right. The randomness is real, but the correlation is absolute. Imagine trying to explain this to someone from the classical world of Newton and Galileo. You might say, imagine two coins that always land opposite to each other, no matter how far apart you flip them. Sounds impossible, doesn't it? Yet this is precisely what nature does at the quantum scale, creating correlations that seem to mock our intuitive understanding of how separate objects should behave. The experimental verification of these correlations requires extraordinary precision. Scientists must ensure that their measurements happen quickly enough that no signal traveling at the speed of light could coordinate the particles' responses. They must eliminate every possible source of bias or communication between the detection systems, and they must repeat their experiments thousands of times to build statistical confidence. One of the most elegant demonstrations uses what physicists call the aspect experiment, named after Alan Aspect, who refined the technique in the 1980s. Entangled photons are sent to detectors positioned far apart, while the photons are in flight. The experimenters randomly change the orientation of their polarizers, ensuring that no signal could influence both measurements. The results are always the same. The correlations persist, regardless of distance, regardless of timing, regardless of any attempt to break the connection. The universe seems to maintain a cosmic bookkeeping system that ensures entangled particles always give correlated results, even when separated by distances that would require faster than light communication to coordinate. This creates what philosophers call the measurement problem in quantum mechanics. The act of observation doesn't just reveal a property that was already there. It actually forces the particle to choose a property from a range of possibilities. But if observation creates reality rather than merely revealing it, what happens when we observe entangled particles simultaneously? Some interpretations suggest that measuring one particle instantly collapses the quantum state of both forcing the distant partner to choose a complementary property. Others propose that both particles existed in a shared superposition until the moment of measurement, when the entire entangled system collapsed into a definite state, regardless of which interpretation you prefer. The result is the same perfectly correlated randomness. This leads us to one of the most mind-bending aspects of quantum entanglement: the question of when the correlation actually occurs. Does the northern photon's choice instantly influence its southern partner, or do both particles somehow choose simultaneously in a coordinated quantum dance that transcends our ordinary understanding of causality? Recent experiments have pushed this question to its limits by creating entangled states between particles separated by satellite links spanning continents. When scientists in Vienna measure their photon, the correlation with its partner in Beijing appears instantaneous. Despite the vast distance involved, this suggests that whatever mechanism underlies entanglement operates outside our normal concepts of space and time. But perhaps the most remarkable aspect of these experiments is their consistency. Quantum entanglement works the same way whether the particles are separated by millimeters or kilometers, whether they're photons, electrons, or entire atoms, whether the experiment happens in a basement laboratory or using satellites orbiting Earth. The correlations persist with mathematical precision. This universality suggests that entanglement reveals something fundamental about the nature of reality itself. Not just an odd quirk of quantum mechanics, but a basic feature of how the universe operates at its deepest level. It's as if nature has written correlation into the very fabric of existence, creating connections that transcend the boundaries we perceive between separate objects. The implications extend far beyond physics into philosophy and our understanding of consciousness. If particles can share states across vast distances, what does this mean for our sense of individual identity? Are we truly separate beings or aspects of a more interconnected reality? These questions have no easy answers, but they remind us that science often leads us to mysteries as profound as any poetry. As we drift deeper into this quantum wonderland, we begin to see that entanglement is not just about particles and measurements. It's about the fundamental structure of information itself in the quantum world. Information doesn't simply exist in one place or another. It can be distributed across space in ways that create new possibilities for computation, communication, and understanding. Quantum computers harness this distributed information to perform calculations that would be impossible for classical machines by manipulating entangled quantum bits. These devices can explore multiple solutions simultaneously, like having thousands of researchers working on the same problem in parallel dimensions, each exploring different possibilities until the correct answer emerges. The technology is advancing rapidly from early experiments with single entangled pairs to networks of dozens of connected particles. Scientists are building the infrastructure for a quantum internet where information could be transmitted with perfect security and computational problems could be solved with unprecedented efficiency. Yet, for all these practical applications, the fundamental mystery remains. Why does nature allow particles to be connected in this way? What evolutionary advantage could there be to a universe where distant objects share quantum states? Some scientists speculate that entanglement might be essential for the stability of matter itself, helping to bind particles into atoms and atoms into molecules. Others suggest that quantum correlations might play a role in biological processes from photosynthesis to possibly even consciousness itself. While these ideas remain speculative, they hint at the possibility that the spooky connections we observe in laboratories might be operating throughout the natural world in ways we're only beginning to understand. As night deepens and our journey through the quantum realm continues, remember that every photon of light reaching your eyes, every electron flowing through your device, every atom in your body has potentially been entangled with countless others throughout cosmic history. You are part of an intricate web of quantum correlations that spans the universe, connecting you to stars that died billions of years ago and particles that won't be born for eons to come. This isn't mysticism, it's mathematics. The equations of quantum mechanics describe a universe where separation is sometimes an illusion, where correlation transcends causation, and where the act of observation plays a fundamental role in creating the reality we experience. It's a universe far stranger and more wonderful than our ancestors ever imagined. Yet it's the universe we call home. In our next gentle exploration, we'll delve even deeper into the philosophical implications of quantum entanglement, examining how this phenomenon challenges our most basic assumptions about reality, causality, and the nature of existence itself. We'll discover how the simple act of measurement can create the very properties it seems to reveal, and why some of the greatest minds in physics have spent their careers trying to understand what it all means. But perhaps The most unsettling revelation about quantum entanglement is what it suggests about the nature of measurement itself. In our everyday world, measurement seems straightforward. You point an instrument at something, and it tells you what's already there. A thermometer reveals the temperature of a room. A scale shows the weight of an apple. Simple observations of pre existing properties. Yet in the quantum realm, measurement takes on an almost mystical quality. The act of observation doesn't merely reveal what was already there, it participates in creating the very reality. It observes. When you measure the spin of an entangled particle, you're not discovering a hidden property. You're forcing the universe to choose from a menu of possibilities. This leads to what physicists call the collapse of the wave function, a rather dramatic name for what might be the most profound event in all of physics. Imagine a wave of pure possibility spreading through space, containing all potential outcomes simultaneously. Then, suddenly, upon measurement, this wave collapses into a single, definite reality, like a symphony of infinite notes, resolving into a single clear tone. The implications are staggering if measurement creates reality rather than revealing it. Then what existed before anyone was around to observe anything? Did the universe spend billions of years in a state of quantum superposition, waiting for the first conscious observer to collapse its wave function into definite existence? Or does measurement require something more subtle than consciousness? Some interpretations of quantum mechanics suggest that any interaction capable of extracting information counts as a measurement. In this view, the universe is constantly measuring itself through countless quantum interactions, each collision between particles, each absorption of light, each tiny perturbation potentially collapsing nearby wave functions into definite states. Others propose that consciousness plays a special role, that the universe remains in superposition until observed by a mind capable of awareness. This interpretation leads to fascinating questions about the relationship between physics and consciousness. Does awareness create reality, or does reality create the possibility of awareness? These philosophical puzzles become even more intriguing when we consider entangled systems. If measuring one particle instantly affects its distant partner, what does this tell us about the nature of information itself? Does information travel faster than light, or does the concept of information need to be redefined in quantum terms? Einstein famously worried about this apparent violation of relativity. His theory of special relativity established that nothing, not matter, not energy, not information, can travel faster than light. Yet quantum entanglement seems to create instant correlations across arbitrary distances. How can both theories be correct? The answer lies in a subtle distinction between correlation and communication. While entangled particles are indeed correlated, their connection cannot be used to send messages. The randomness of quantum measurement ensures that neither observer can control what result they obtain. They can only discover perfect correlations after comparing their random results. Imagine two friends playing a cosmic game of chance, each flipping coins that always land opposite to each other, while the correlation is perfect and instantaneous. Neither friend can influence their coin to deliver a specific message. They can only marvel at the mysterious connection. After the fact, this preservation of relativity through randomness reveals something profound about the structure of reality. The universe seems designed to maintain certain fundamental principles while allowing for seemingly impossible phenomena. Quantum mechanics and relativity coexist not by ignoring each other, but by respecting each other's boundaries in elegant and unexpected ways. Modern experiments have pushed these boundaries to extraordinary limits. Scientists have created entangled states between particles separated by thousands of kilometers using ground based fiber optic networks and satellite links. They've demonstrated quantum correlations between different types of particles, photons and atoms matter, and light bridging the gap between different realms of physics. One particularly beautiful experiment involves what physicists call quantum teleportation, a process that sounds like science fiction but operates according to well understood quantum principles. While you cannot teleport a person or even a single particle, you can teleport the quantum state of one particle to another using entanglement as a bridge. Here's how it works. Imagine three particles, two of which are entangled. If you perform a special measurement on the third particle and one of the entangled pair, you can transfer the quantum state of the third particle to the remaining entangled particle. The original state is destroyed in the measurement, but its exact replica appears at the distant location. This isn't faster than light communication because you still need to send classical information about your measurement results to complete the teleportation process. But it does demonstrate that quantum information can be transported across space in ways that classical physics never imagined possible. The applications of quantum teleportation extend far beyond laboratory curiosities. Quantum networks of the future might use teleportation to distribute quantum information between processors, enabling unprecedented computational power. Quantum communication systems might use teleportation to create unbreakable encryption schemes that guarantee message security. Yet, for all these practical applications, the deeper mystery remains: what is quantum information and how does it differ from classical information? Classical information can be copied perfectly. You can photocopy a document or duplicate a digital file without losing any content. But quantum information cannot be cloned perfectly. Copying a quantum state necessarily disturbs the original. This no cloning theorem, as physicists call it, has profound implications for privacy and security. If quantum information cannot be copied, then any attempt to intercept it necessarily leaves traces. Quantum cryptography exploits this feature to create communication channels that automatically detect eavesdropping attempts. The theorem also suggests something fundamental about the nature of reality itself. If information is truly fundamental to the universe, as some physicists propose, then the quantum no cloning principle might be one of the deepest laws of nature, protecting the integrity of information and preventing paradoxes that could arise from perfect copying. These considerations lead us into the realm of quantum field theory, where particles are understood not as discrete objects, but as excitations and underlying fields that permeate all of space. In this view, entanglement becomes even more mysterious because the fields themselves can become entangled, creating correlations that span the entire universe. Imagine the vacuum of space not as empty nothingness, but as a seething foam of quantum activity where virtual particles constantly pop into existence and annihilate each other. These quantum fluctuations create an intricate web of correlations that connects every region of space to every other region, in ways we're only beginning to understand. Some theories suggest that this quantum foam might be the source of space time itself, that the geometry of the universe emerges from the entanglement structure of quantum fields. In this view, space and time are not fundamental but emergent properties arising from more basic quantum correlations. If this sounds like the stuff of philosophy rather than physics, consider that these ideas are driving some of the most active research in theoretical physics. Today, scientists are exploring how quantum entanglement might be related to the geometry of spacetime, how black holes process quantum information, and whether the universe itself might be a vast quantum computer processing information through entangled correlations. The mathematics describing these phenomena is elegant yet mind-bending equations that treat space and time as variables rather than fixed backgrounds that describe information flowing through networks of quantum correlations that suggest reality might be far more fluid and interconnected than our everyday experience indicates as we drift through these conceptual landscapes. It's worth pausing to appreciate the journey from Einstein's skeptical, spooky action at a distance to today's sophisticated understanding of quantum networks and information theory. What began as a philosophical objection has become the foundation for revolutionary technologies and new ways of understanding reality itself. The story is far from over. Each new experiment reveals fresh mysteries about the nature of quantum correlations. Each theoretical advance opens new questions about the relationship between information, consciousness, and reality. Each technological breakthrough brings us closer to applications that could transform how we compute, communicate, and understand our place in the cosmos. Quantum entanglement remains one of science's most beautiful paradoxes, a phenomenon that seems impossible yet works perfectly, that challenges our intuitions yet obeys precise mathematical laws, that connects particles across cosmic distances, yet respects the fundamental speed limit of the universe. In our continuing exploration, we'll delve deeper into the philosophical implications of these quantum mysteries, examining how entanglement challenged our concepts of causality, locality, and the nature of existence itself. We'll discover how the quantum world might be teaching us profound lessons about the interconnected nature of reality and why some of the greatest minds in physics continue to wrestle with questions that seem to blur the line between science and philosophy. For now, though, let yourself drift with the wonder of it all, knowing that in laboratories around the world tonight, scientists are creating quantum correlations that span continents, manipulating information in ways that would have seemed magical just decades ago, and slowly unveiling the deepest secrets of a universe far stranger and more beautiful than anyone ever dared imagine. And so we find ourselves standing at the edge of perhaps the most profound philosophical chasm that quantum entanglement has opened, the question of what reality actually is when no one is looking. If particles exist in superposition until measured, if their properties emerge only through observation, then what can we say about the universe during those vast epochs before consciousness arose to witness it? This question has tormented physicists and philosophers for nearly a century, leading to interpretations of quantum mechanics that sound more like competing creation myths than scientific theories. Some suggest the universe branches into parallel realities, with every quantum measurement creating infinite worlds where every possibility plays out simultaneously. Others propose that consciousness itself plays a fundamental role in collapsing quantum possibilities into definite outcomes. Consider the famous thought experiment of Schrodinger's cat, a feline placed in a box with a quantum device that has a 50% chance of releasing poison. The cat, according to quantum mechanics, should exist in a superposition of both alive and dead until someone opens the box to observe it. Schrödinger intended this as a critique of quantum theory, but instead, it became one of its most enduring symbols. The cat paradox reveals the strange boundary between the quantum world of possibilities and our everyday world of definite outcomes, somewhere between the microscopic realm of atoms and the macroscopic world of cats. Quantum superposition gives way to classical reality. But where exactly does this transition occur and what causes it? Some physicists propose that the transition happens naturally through a process called decoherence when quantum systems interact with their environment. The delicate superpositions that allow for multiple simultaneous states become entangled with countless other particles, creating a web of correlations so complex that the system effectively loses its quantum coherence. Imagine a single photon maintaining perfect superposition as it travels through empty space. But the moment it encounters even a single molecule of air, its quantum state becomes entangled with that molecule, then with others, creating an exponentially growing network of correlations that transforms quantum possibility into classical certainty. This environmental decoherence might explain why we don't observe quantum superposition in everyday objects. They're constantly interacting with air molecules, light photons, and countless other particles that destroy the delicate quantum states before we can observe them. The cat in Schrodinger's box would decohere almost instantly, not because someone observed it, but because it cannot avoid interacting with its environment. Yet decoherence doesn't fully resolve the measurement problem. It explains why superposition disappears, but not why we observe one particular outcome rather than another when we measure an entangled particle. Why does it choose spin up rather than spin down? Why does reality select one possibility from the infinite menu of quantum options? This leads us to what might be quantum mechanics' most unsettling implication, that the act of observation might be fundamentally creative rather than merely revelatory, that consciousness, or at least the capacity for measurement, might play an active role in shaping reality itself, not through mystical influence, but through the basic physics of information extraction. Recent experiments have pushed this boundary even further. Scientists have created quantum systems that seem to remember being observed even when the observation is erased afterward. These quantum eraser experiments suggest that the relationship between measurement and reality is even stranger than we imagined, with effects that seem to propagate backward through time. Imagine conducting an experiment where you can choose whether to observe which path a particle took through a double slit apparatus. But you make this choice after the particle has already passed through the slits. Quantum mechanics predicts, and experiments confirm that your future choice affects the particle's past behavior, as if the universe waits to see what you'll decide before determining what actually happened. These temporal paradoxes don't violate causality. In any practical sense, you still cannot send information backward in time or change the past in ways that create grandfather paradoxes. but they do suggest that our ordinary concepts of past, present, and future might be insufficient to describe quantum reality. The implications extend beyond physics into questions about the nature of time itself. If quantum effects can seemingly influence the past, then perhaps time is not the linear flowing river we imagine, but something more, like a landscape where past, present, and future coexist in complex relationships that we're only beginning to understand. Some theories propose that quantum entanglement might be the key to understanding time's true nature, that the correlations between entangled particles create a kind of quantum geometry that gives rise to our perception of temporal flow. In this view, time doesn't pass. We simply experience different slices of a timeless quantum reality. These ideas connect to some of the most ambitious theories in modern physics, attempts to unify quantum mechanics with general relativity that might reveal space and time to be emergent properties of more fundamental quantum relationships. String theory, loop quantum gravity, and other approaches all suggest that reality at its deepest level might be far more abstract and mathematical than our everyday experience indicates. Yet, for all these theoretical speculations, quantum entanglement remains grounded in practical reality. Every day, scientists and engineers work with entangled systems to build quantum computers, develop secure communication networks, and probe the fundamental limits of measurement and information processing. The quantum internet is already taking shape with entangled photons distributed through fiber optic networks connecting quantum processors across continents. These networks will enable new forms of computation that could revolutionize everything from drug discovery to weather prediction. By harnessing the parallel processing power of quantum superposition, quantum sensors that exploit entanglement can detect gravitational waves, measure magnetic fields with unprecedented precision, and peer into biological systems without disturbing their delicate quantum processes. Medical imaging devices based on quantum technology might soon provide detailed pictures of the human brain while it thinks, revealing the neural correlates of consciousness with exquisite detail. Perhaps most intriguingly, some researchers are exploring whether quantum effects might play a role in biological processes themselves. Photosynthesis, the process by which plants convert sunlight into chemical energy, seems to use quantum superposition to explore multiple energy pathways, simultaneously finding the most efficient route. With quantum precision, bird navigation might rely on quantum entanglement in specialized proteins that act as biological compasses sensitive to Earth's magnetic field. Even the human sense of smell might operate through quantum tunneling effects that allow us to distinguish between molecules based on their vibrational frequencies rather than just their shape. If these biological quantum effects are real, then the boundary between the quantum world and everyday life becomes even more blurred. We might literally be quantum beings living in a quantum universe using quantum processes in ways we're only beginning to understand. Our thoughts, emotions, and experiences might emerge from quantum correlations in the neural networks of our brains. This possibility leads to some of the most speculative yet fascinating questions. In modern science, could consciousness itself be a quantum phenomenon that requires entanglement and superposition to exist? Might our sense of unified awareness emerge from quantum correlations that bind billions of neurons into a single experiencing system These questions remain highly controversial, with most neuroscientists skeptical that warm, wet biological systems could maintain the delicate quantum states required for such effects. Yet the questions persist because consciousness remains one of science's deepest mysteries, and quantum mechanics continues to surprise us with its applicability to unexpected domains. As we drift deeper into these quantum mysteries, it's worth remembering that we're exploring ideas that would have seemed like pure fantasy just a century ago. The notion that particles could be in multiple places simultaneously. That measurement creates, rather than reveals, properties that distant objects could be instantaneously correlated. All of these concepts emerged from careful mathematical analysis and precise experimental verification. The story of quantum entanglement is ultimately a story about the power of human curiosity and ingenuity to uncover nature's deepest secrets through patient observation, careful reasoning, and bold theoretical leaps. Scientists have revealed a universe far stranger and more wonderful than anyone imagined. Yet the story is far from complete. Each new experiment raises fresh questions. Each theoretical advance opens new possibilities for understanding reality. Each technological breakthrough brings us closer to applications that could transform civilization itself. Quantum entanglement has already taken us from philosophical speculation to practical technology, but its full implications may not be understood for generations to come. In our final exploration of this quantum wonderland, we'll examine what quantum entanglement might mean for the future of human knowledge and capability, how it might reshape our understanding of consciousness reality and our place in the cosmos, and why this spooky action at a distance might ultimately prove to be one of the most important discoveries in the history of science for now. Though let yourself rest in the quiet amazement of it all, knowing that somewhere in the universe, tonight particles are dancing their quantum dance, maintaining correlations that transcend space and time, proving once again that reality is far more beautiful, mysterious, and interconnected than our wildest dreams could ever imagine. The mysteries of quantum entanglement become even more profound when we consider how this phenomenon might reshape our understanding of information itself. In our classical world, information seems straightforward: bits and bytes, letters on a page, sounds in the air. But quantum information operates by entirely different rules, rules that seem to blur the very boundaries between knowledge and reality. When a quantum computer processes information, it doesn't simply manipulate ones and zeros like its classical cousins. Instead, it harnesses the ghostly power of superposition to explore multiple computational paths simultaneously. Imagine trying to solve a maze, not by testing one route at a time, but by walking all possible paths at once until the correct solution emerges from the quantum mist. This parallel processing capability stems directly from entanglement by creating networks of interconnected quantum bits. Scientists can build systems where each calculation influences every other calculation in ways that would be impossible with classical information. The result is computational power that grows exponentially with each additional quantum bit added to the system. But perhaps the most beautiful aspect of quantum information is its fundamental fragility. Unlike classical data, which can be copied endlessly without degradation, quantum information cannot be perfectly cloned. The very act of trying to duplicate a quantum state necessarily disturbs the original, creating a kind of cosmic copyright protection built into the fabric of reality itself. This quantum no cloning theorem, as physicists call it, has profound implications for privacy and security. If information cannot be copied without detection, then any attempt to eavesdrop on quantum communication automatically reveals itself to the legitimate parties. It's as if nature has provided us with an unbreakable encryption system written in the language of the universe itself. Quantum cryptography exploits this principle to create communication channels that are provably secure, not because we believe they cannot be broken, but because the laws of physics guarantee that any attempt to break them will be detected. The security doesn't rely on mathematical complexity or computational difficulty, but on the fundamental structure of quantum reality. Imagine two parties sharing entangled particles as a kind of quantum telephone. When one person encodes a message by manipulating their particle, the correlation ensures that the other person's particle changes in a predictable way. But if anyone tries to intercept the message by observing the particles in transit, they necessarily disturb the entanglement, revealing their presence. This quantum eavesdropping detection has already moved from laboratory curiosity to practical application. Quantum key distribution networks operate in several countries, allowing banks, governments, and corporations to exchange sensitive information with unprecedented security. The age of quantum communication has quietly begun, yet the implications extend far beyond secure messaging. Some physicists speculate that quantum information might be the fundamental currency of reality itself, that the universe at its deepest level consists not of matter and energy, but of quantum information processing itself through vast networks of entangled correlations. In this view, particles are not tiny objects bouncing around in space, but rather information processing nodes in a cosmic quantum computer. Each interaction, each measurement, each moment of entanglement represents a calculation in an ongoing universal computation that somehow gives rise to the rich tapestry of experience we call reality. This information theoretic view of physics leads to startling questions about the nature of existence. If the universe is fundamentally computational, what is it computing and for whom? If reality emerges from information processing, what lies beneath the processing itself? These questions push us to the very edge of scientific understanding. Some researchers have proposed that consciousness itself might be understood as a particular kind of information processing that requires quantum coherence to function properly. In this speculative view, your thoughts, emotions, and experiences emerge from quantum correlations between neurons, creating a unified stream of awareness from billions of separate cellular computations. While such ideas remain highly controversial, they illustrate how quantum entanglement continues to challenge our most basic assumptions about mind matter and the relationship between them. The phenomenon that Einstein dismissed as spooky action at a distance has become a lens through which we might glimpse the deepest secrets of consciousness itself. The technological implications are equally staggering. Quantum sensors that exploit entanglement can detect changes in gravitational fields, magnetic fields, and other physical quantities, with sensitivity approaching the fundamental limits imposed by quantum mechanics. These devices might reveal gravitational waves from the birth of the universe, detect dark matter particles, or peer into living cells without disturbing their delicate biological processes. Medical applications of quantum technology are particularly promising. Quantum magnetic resonance imaging might provide detailed pictures of the brain while it thinks, revealing the neural correlates of consciousness with unprecedented clarity. Quantum sensors might detect cancer cells by their subtle magnetic signatures, or monitor the quantum effects that some researchers believe play a role in photosynthesis and other biological processes. The pharmaceutical industry is already exploring how quantum computers might revolutionize drug discovery by simulating molecular interactions with perfect accuracy rather than relying on approximations. Classical computers must use to model quantum systems. Quantum processors could design new medicines by directly calculating how different compounds would interact with disease targets. Climate science, too, might benefit from quantum computation. The Earth's atmosphere is a complex quantum mechanical system where countless molecular interactions determine weather patterns and climate trends. Quantum computers might provide the computational power needed to create truly accurate climate models, helping humanity understand and respond to environmental challenges. Yet, for all these practical applications, the most profound impact of quantum entanglement might be philosophical rather than technological, by revealing the deeply interconnected nature of reality. This phenomenon challenges our ordinary sense of separateness and independence, suggesting that the boundaries we perceive between objects might be more fluid than we imagine. This doesn't mean that everything is connected in some mystical New Age sense, but it does suggest that our classical intuitions about locality and separability might be incomplete approximations to a more subtle quantum reality where correlation and connection operate according to principles we're still struggling to understand. The journey from Einstein's skeptical objection to today's quantum technologies illustrates the power of scientific inquiry to transform philosophical puzzles into practical tools. What began as an abstract debate about the completeness of quantum mechanics has evolved into engineering challenges and commercial opportunities that might reshape civilization. Quantum startups are sprouting in technology centers around the world, developing everything from quantum computers and communication systems to sensors and simulation software. Governments are investing billions in quantum research, recognizing that nations with advanced quantum capabilities might enjoy significant advantages in computing cryptography and scientific discovery. Yet the field remains in its infancy, comparable perhaps to classical computing in the 1950s, when room-sized machines could barely perform calculations that today's pocket calculators handle effortlessly. The quantum computers of today are delicate laboratory instruments requiring extreme cooling and careful isolation from environmental interference. But progress is accelerating rapidly. Each year brings new records for quantum coherence, times numbers of entangled particles, and distances over which quantum correlations can be maintained. The theoretical foundations are solid, and the engineering challenges, while formidable, are being systematically overcome by teams of dedicated researchers and entrepreneurs. The quantum internet might be the next great leap forward. Networks of entangled particles distributed through fiber optic cables and satellite links could enable new forms of distributed computation where quantum processors around the world collaborate on problems too complex for any single machine to solve. Imagine weather simulations that harness quantum processors on every continent, each contributing its computational power to model local atmospheric conditions, while quantum entanglement ensures that the global calculation remains coherent, or drug discovery projects that use quantum computers in laboratories worldwide to explore different molecular configurations simultaneously. These applications might seem like science fiction, but the underlying physics is well understood, and the engineering challenges are being addressed systematically. The quantum revolution is not a distant possibility, but an ongoing transformation that has already begun in research laboratories and technology companies around the world as we near the end of our gentle journey through the quantum realm. It's worth reflecting on what quantum entanglement has taught us about the nature of scientific discovery itself. This phenomenon emerged not from a single brilliant insight, but from decades of patient theoretical work, careful experimentation, and gradual refinement of our understanding. The story illustrates how science advances through the interplay between theory and experiment, between mathematical formalism and physical intuition, between skeptical questioning and open minded exploration. Einstein's objections to quantum entanglement were not obstacles to progress, but essential challenges that ultimately deepened our understanding. Today's quantum technologies exist because generations of physicists refused to accept easy answers to hard questions. They developed increasingly sophisticated mathematical tools, designed ever more precise experiments, and gradually constructed a theoretical framework capable of describing nature's most subtle phenomena. The process continues as new experiments push the boundaries of what we can observe and control. New theories attempt to explain the deepest puzzles of quantum mechanics, and new technologies emerge from the marriage of fundamental physics and practical engineering. Quantum entanglement remains at the center of these developments. In our final moments together, let us simply marvel at the extraordinary journey we've taken from the apparent impossibility of action at a distance to the practical reality of quantum computers and communication networks, from philosophical debates about the nature of reality to engineering challenges in building quantum devices. The particles dancing their mysterious quantum dance across cosmic distances have led us to technologies that might transform civilization and insights that challenge our deepest assumptions about the nature of existence itself. They remind us that the universe is far stranger, more beautiful, and more interconnected than our everyday experience suggests. Quantum entanglement has shown us that reality operates according to principles that seem impossible yet work perfectly, that connection and correlation can transcend space and time in ways that respect the fundamental laws of physics while defying our classical intuitions about how separate objects should behave. As you drift towards sleep tonight, remember that you are part of this quantum universe, that the atoms in your body have been entangled with countless others throughout cosmic history, that you exist within a web of correlations that spans from the smallest scales to the largest, connecting you to the stars and to the fundamental processes that give rise to consciousness itself. The spooky action at a distance that once troubled Einstein has become a window into the deepest nature of reality, revealing a universe where information and correlation dance together in patterns of breathtaking complexity and beauty, where the act of observation participates in creating the very reality it seeks to understand. Sweet dreams, fellow traveler, in this quantum cosmos, where mystery and wonder await around every corner, where the impossible becomes routine, and where the simple act of looking at the world with curiosity and care can unveil secrets that transform our understanding of everything we thought we knew about existence itself. Perhaps the most remarkable aspect of our quantum journey is how it mirrors the very phenomenon we've been exploring. The deeper we peer into quantum entanglement, the more we ourselves become entangled with its mysteries. Like particles that cannot return to their original state once they've interacted, our understanding of reality has been permanently altered by this encounter with the impossible made manifest. Consider for a moment the extraordinary fact that human consciousness has managed to discover and harness phenomena that seem to operate outside the boundaries of everyday experience. We've learned to create correlations that transcend space, manipulate information that cannot be copied, and build technologies based on principles that would have seemed like pure magic to our ancestors. This achievement speaks to something profound about the relationship between mind and reality. The universe has somehow given rise to beings capable of understanding its own deepest secrets. Conscious observers who can not only witness quantum entanglement, but actively create and control it for practical purposes. We are quantum mechanics, made manifest walking embodiments of the very principles we study. The philosophical implications ripple outward like waves from a stone dropped in a still pond if consciousness can discover and manipulate quantum phenomena. What does this tell us about the nature of consciousness itself? Are we separate observers studying an external reality, or are we part of the quantum fabric? We're attempting to understand. Some researchers have begun exploring whether the brain itself might be a quantum system that uses entanglement and superposition to bind billions of neurons into a unified conscious experience. While this remains highly speculative, the possibility is tantalizing. Could our sense of being a single experiencing self emerge from quantum correlations that connect every neuron in our brains? Imagine if conscious experience requires quantum coherence across large networks of brain cells. Your thoughts, emotions, and memories might literally depend on the same spooky action at a distance that connects particles across the cosmos. Consciousness could be nature's most sophisticated application of quantum entanglement, creating unified awareness from distributed neural processing. These ideas remain at the frontier of scientific speculation, but they illustrate how quantum entanglement continues to challenge our understanding of mind matter and the relationship between them. The phenomenon that began as a philosophical puzzle has become a lens through which we might glimpse the deepest mysteries of existence. As quantum technologies mature, we can expect even more startling applications. Quantum computers might simulate consciousness itself, helping us understand how subjective experience emerges from objective physical processes. Quantum sensors might detect the subtle electromagnetic fields generated by neural activity, revealing the quantum signature of thought itself. The medical applications alone could revolutionize human health. Quantum imaging techniques might peer into living brains without disturbing their delicate quantum processes, showing us consciousness in action with unprecedented detail. Early detection of neurological diseases might become possible by monitoring the quantum coherence of neural networks. But perhaps the most profound application lies in the realm of human connection. If consciousness does indeed depend on quantum entanglement, then the boundaries between separate minds might be more fluid than we imagine shared. Quantum states between different brains might create new forms of communication and understanding. Imagine technologies that could create quantum entanglement between neural networks, allowing direct sharing of thoughts, emotions, and experiences, not through crude brain computer interfaces, but through the subtle quantum correlations that already bind particles across the universe, science fiction perhaps, but no more impossible than the quantum computers and communication networks that already exist. These possibilities remind us that we're still in the early chapters of the quantum story. What we've discovered so far might be just the beginning of a transformation that could reshape not only technology, but our understanding of what it means to be human conscious beings in a quantum universe. The journey from Einstein's skeptical objection to today's quantum technologies has taken less than a century, suggesting that the next century might bring advances we can barely imagine: quantum biology, quantum consciousness, quantum theories of everything that unite the smallest scales with the largest and elegant mathematical frameworks. Yet, for all these future possibilities, the most beautiful aspect of quantum entanglement might simply be what it tells us about the nature of reality. Right now, in this moment, the universe is far more interconnected, subtle, and mysterious than our everyday experience suggests. Every particle interaction, every measurement, every moment of conscious observation participates in an ongoing cosmic dance of correlation and connection. The randomness that troubled Einstein has revealed itself to be not chaos, but a deeper kind of order where individual events remain unpredictable while collective patterns emerge with mathematical precision. It's as if the universe maintains perfect books, keeping track of countless quantum correlations while allowing each moment to unfold with spontaneous creativity. This balance between order and chaos, determinism and freedom, might be the key to understanding not just quantum mechanics, but the nature of existence itself. We live in a universe that is neither completely predictable nor entirely random, but something more subtle and beautiful, a realm where possibilities become actualities through the mysterious alchemy of observation and interaction. Quantum entanglement has taught us that the act of looking at the world changes both the world and the observer. In the process of studying quantum correlations, we've become entangled with the phenomena. We investigate our instruments, our theories, our understanding, all shaped by the quantum systems we seek to comprehend. This recursive relationship between observer and observed suggests that science itself might be a quantum phenomenon where the act of investigation creates the very reality it attempts to describe, not through mystical influence, but through the fundamental physics of information exchange between conscious systems and quantum environments as we approach the gentle conclusion of our quantum odyssey. It's worth pausing to appreciate the extraordinary journey we've shared together, from the apparent impossibility of instant correlations across vast distances to practical technologies that harness these correlations for computation, communication, and sensing. We've seen how quantum entanglement challenges our most basic assumptions about locality, causality, and the nature of information itself. how it suggests that reality might be far more fluid and interconnected than our classical intuitions indicate, and how it opens possibilities for technologies that could transform civilization. Yet perhaps the most important lesson is the reminder that the universe is far stranger and more wonderful than we ever dared imagine, that beneath the surface of everyday experience lies a realm of infinite possibility where particles dance together across cosmic distances, where observation participates in creating reality, and where consciousness itself might emerge from quantum correlations. The spooky action at a distance that once seemed impossible has become a window into the deepest nature of existence, revealing a cosmos where mystery and meaning intertwine in patterns of breathtaking beauty and complexity, where the simple act of curious inquiry can unveil secrets that transform our understanding of everything as you settle into the quiet comfort of approaching sleep. Remember that you are part of this quantum tapestry, that every atom in your body has been shaped by quantum interactions throughout cosmic history, that you exist within a web of correlations connecting you to distant stars, ancient supernovas, and future generations yet to be born. The boundaries between self and cosmos observer and observed knower and known become beautifully blurred in the quantum realm, suggesting that separation itself might be a useful fiction rather than a fundamental truth. We are not isolated individuals struggling alone in an indifferent universe, but interconnected aspects of a single quantum reality tonight, as dreams begin to weave their own mysterious patterns in your sleeping mind. Consider the possibility that consciousness itself might be quantum entanglement made manifest the universe, becoming aware of itself through billions of interconnected neural networks, each contributing to the grand symphony of cosmic self understanding. The particles that once puzzled Einstein continue their eternal dance, maintaining correlations that transcend space and time, proving once again that reality is far more beautiful, mysterious, and interconnected than our wildest dreams could ever imagine. And in that quantum dance, we find not just the secrets of the physical world, but glimpses of the deepest truths about existence, consciousness, and the magnificent improbability of being aware in an aware universe. Sweet dreams, fellow quantum traveler in this cosmos, where every moment brings new mysteries to explore, where the impossible becomes routine, and where the gentle act of wondering about the nature of reality reveals that we ourselves are among the universe's most remarkable quantum phenomena. As we drift deeper into this quantum reverie, there's something almost poetic about how our exploration of entanglement mirrors the very phenomenon we've been contemplating. The more we understand these mysterious connections, the more we ourselves become connected to the profound implications they carry, like gentle ripples spreading across the still surface of human knowledge. Picture, if you will, the laboratories scattered across our planet tonight, where dedicated researchers are carefully coaxing photons into their quantum dance, creating correlations that will persist across continents. In Vienna, a physicist adjusts the angle of a crystal, splitting light into entangled pairs. In Beijing, her colleague prepares to receive those ghostly partners, not knowing that their combined work will push the boundaries of what we thought possible about the nature of connection itself. These scientists, working in their quiet dedication, are modern alchemists, transforming the impossible into the inevitable. They've learned to speak the language of particles, to negotiate with probability itself, creating states of matter that exist in the delicate balance between being and not being, between here and there, between now and forever. The beauty of their work lies not just in its technical precision, but in its fundamental optimism about human understanding. Each experiment represents an act of faith that the universe, despite its strangeness, operates according to principles we can discover and eventually comprehend. It's a testament to the remarkable fact that consciousness has evolved to the point where it can contemplate its own quantum foundations. But perhaps what makes quantum entanglement so compelling isn't just its scientific implications, but the way it seems to whisper something profound about the nature of relationship itself. In a world where we so often feel isolated, disconnected from one another and from the cosmos that birthed us, quantum mechanics offers a different story entirely. Consider the carbon atoms in your body, forged in the nuclear furnaces of ancient stars. These atoms have journeyed across billions of years and countless light years to become part of your being. Along the way, they've interacted with countless other particles, creating a web of quantum correlations that connects you, quite literally, to the far reaches of space and time. You are not a separate entity observing the universe from the outside. You are the universe observing itself from the inside, a temporary arrangement of quantum fields that has somehow achieved the remarkable feat of self awareness. The atoms in your left hand were once part of different stars than those in your right hand, yet here they are, collaborating in the magnificent symphony of your existence. This perspective transforms our understanding of loneliness itself. In the quantum view, true isolation is impossible. Every particle that has ever interacted with another remains forever changed by that encounter, carrying within its quantum state a kind of memory of the connection. The universe is not a collection of separate objects, but a single, interconnected whole, temporarily expressing itself through the patterns we call particles, people, and planets. The implications ripple outward into every aspect of human experience. Love, perhaps, takes on new meaning when we consider that the very atoms of two people in embrace have been quantum entangled with particles throughout the cosmos. The boundaries between lover and beloved become beautifully blurred, not through romantic metaphor, but through the fundamental physics of reality itself. Art, too, finds new resonance in the quantum realm. When a painter captures light on canvas, she's working with photons that may have been entangled with others, now scattered across the galaxy. The colors we perceive emerge from quantum processes in our visual systems, where electrons dance between energy levels in patterns that create the rich tapestry of human perception. Music becomes even more mysterious when we consider that sound waves are disturbances in quantum fields, propagating through space as collective excitations of countless particles. When you listen to a symphony, you're experiencing the universe expressing itself through the coordinated quantum motion of matter, creating patterns of compression and rarefaction that somehow translate into beauty, emotion, and meaning. Even language itself might be understood as a quantum phenomenon, where the meaning of words emerges from the complex interactions between neural networks in the speaker's brain and similar networks in the listener's mind. Communication becomes a kind of entanglement between consciousness, where ideas propagate across the space between minds through the subtle correlations of sound and symbol. These poetic interpretations don't diminish the scientific rigor of quantum mechanics, but rather illuminate the profound beauty that emerges when mathematical formalism meets human experience. The equations that describe entanglement are elegant in their precision, yet they point toward mysteries that touch the very heart of what it means to exist as conscious beings in a quantum universe. The future applications of quantum entanglement continue to unfold like a flower blooming in slow motion. Quantum computers, still in their infancy, promise to revolutionize everything from weather prediction to drug discovery. These machines will harness the parallel processing power of superposition to explore solution spaces that classical computers could never navigate. Imagine climate models that can simultaneously explore millions of possible atmospheric configurations, finding patterns and predictions with unprecedented accuracy. Picture pharmaceutical researchers using quantum simulation to design molecules atom by atom, creating medicines tailored to individual genetic profiles with quantum precision. The quantum internet, that network of entangled particles spanning the globe, might enable new forms of human collaboration where distance becomes irrelevant to connection. Scientists in different hemispheres could share quantum states directly, creating a kind of technological telepathy based on the fundamental correlations of reality itself. But perhaps the most intriguing possibility lies in the realm of consciousness research. If the brain does indeed operate as a quantum system, then understanding entanglement might be the key to understanding awareness itself. We might discover that consciousness is not produced by the brain, but rather emerges from the quantum correlations that bind billions of neurons into a unified experiencing system. This could lead to technologies that detect conscious states directly, monitoring the quantum coherence of neural networks to determine levels of awareness, pain, or cognitive function. Medical professionals might use quantum sensors to peer into the minds of patients in comas, detecting subtle signs of consciousness that current methods cannot reveal. The philosophical implications stretch even further. If consciousness requires quantum coherence, then every moment of awareness represents a remarkable achievement against the forces of decoherence that tend to destroy quantum states. Your ability to maintain a unified sense of self while billions of neurons fire in complex patterns might be one of the most sophisticated applications of quantum mechanics in the known universe. This perspective transforms meditation and mindfulness practices into something approaching quantum engineering. When you focus your attention, you might literally be creating quantum coherence across neural networks, binding disparate brain regions into harmonious collaboration. The ancient practices of contemplative traditions might have discovered through inner observation principles that quantum mechanics has only recently begun to understand. Sleep itself becomes a quantum phenomenon in this view. As consciousness fades and dreams begin, the quantum coherence that maintains waking awareness might shift into different patterns, allowing the brain to explore states of being that are impossible during fully coherent wakefulness. Dreams might be excursions into quantum superposition, where the usual rules of logic and causality give way to the fluid possibilities of the quantum realm. The boundary between dreaming and waking consciousness becomes beautifully blurred when we consider that both might be different expressions of the same underlying quantum processes. Perhaps the sense of strangeness we feel upon waking from a vivid dream reflects the transition between different modes of quantum coherence, different ways of organizing the correlations that create subjective experience. These ideas remain highly speculative, dancing at the edge of what current science can verify. Yet they illustrate how quantum entanglement continues to challenge our most basic assumptions about mind, matter, and the relationship between them. What began as a puzzle about particle correlations has evolved into a lens through which we might glimpse the deepest mysteries of existence itself. As the night deepens and our quantum journey draws toward its gentle close, we find ourselves transformed by the encounter with these mysteries. Like particles that cannot return to their original state after interaction, our understanding of reality has been permanently altered by this exploration of the impossible made manifest. The universe revealed through quantum entanglement is not the clockwork cosmos of classical physics, but something far more elegant and mysterious. It's a reality where relationship precedes separation, where correlation transcends causation, where the act of observation participates in creating the very phenomena it seeks to understand. Tonight, as you prepare to surrender consciousness to the quantum realm of dreams, remember that you carry within your very atoms the history of cosmic evolution. You are stardust made conscious, quantum fields temporarily organized into the miraculous pattern of awareness. The particles that compose your being have danced across billions of years to arrive at this moment of contemplation, carrying with them the accumulated correlations of countless interactions. In the morning, when consciousness returns and the quantum coherence of wakefulness reasserts itself, you'll carry with you the knowledge that reality is far stranger and more beautiful than everyday experience suggests. You'll know that beneath the surface of the ordinary world lies a realm where particles maintain eternal connections across infinite distances, where the impossible becomes routine, and where the simple act of looking at the universe with wonder and curiosity reveals that we ourselves are among its most remarkable quantum phenomena. The spooky action at a distance that once troubled Einstein has become a doorway into understanding the profound interconnectedness of all existence. Through that doorway, we glimpse not just the mechanics of quantum correlation, but the deeper truth that separation itself might be the grandest illusion of all. Sweet dreams, fellow traveler in this quantum cosmos, where mystery and meaning dance together in patterns of infinite complexity and beauty, where consciousness and cosmos intertwine in the eternal quantum waltz of existence, becoming aware of itself through the miracle of minds like yours, contemplating the impossible and finding it not only possible, but gloriously, mysteriously, beautifully real. As we settle into the deepest part of our quantum journey, there's something wonderfully paradoxical about how the most abstract concepts in physics can lead us to the most intimate questions about our own existence. The equations that describe entanglement may be written in the austere language of mathematics, but they whisper stories about connection that touch the very heart of what it means to be human in an interconnected universe. Think for a moment about the extraordinary chain of events that brought you to this very instant. The photons carrying these words to your eyes began their journey perhaps from a screen powered by electrons flowing through circuits designed by minds that learned about quantum mechanics from experiments conducted decades ago. Those experiments themselves depended on particles that had been entangled in laboratories by scientists who never could have imagined their work would eventually reach you through this gentle exploration of their discoveries. There's something almost magical about this transmission of understanding across space and time from mind to mind through the medium of quantum phenomena that we're only just beginning to comprehend. You're receiving information that was encoded by manipulating the quantum states of matter, transmitted through electromagnetic fields, and decoded by the quantum processes in your own neural networks. In a very real sense, you're experiencing quantum entanglement in action. The researchers working in quantum laboratories around the world tonight are participating in something that resembles an ancient ritual of discovery. In darkened rooms filled with carefully calibrated instruments, they coax photons and electrons into their quantum dances, creating correlations that will outlast the experiments themselves. These dedicated souls work with the patience of gardeners, nurturing delicate quantum states that exist for mere microseconds, yet reveal truths that will endure for centuries. Their work requires a peculiar combination of technical precision and philosophical openness. They must master the intricate details of laser systems, optical fibers, and detection equipment while remaining comfortable with concepts that seem to defy common sense. It's as if they've learned to think in quantum language, accepting paradox as natural and finding beauty in the impossible. The instruments they use have become increasingly sophisticated, capable of detecting single photons and measuring quantum states with extraordinary precision. Yet, for all their technical complexity, these devices are essentially asking very simple questions of nature. Are you really connected? Do you truly know each other instantaneously? Is the universe as strange as our equations suggest? And nature's answer, delivered through countless careful measurements, remains consistently yes. The correlations persist, the entanglement endures, the quantum world continues to operate according to principles that challenge our deepest intuitions about reality while revealing new layers of elegant mathematical structure. What makes this scientific story so compelling is not just its technical achievements, but the way it illuminates the relationship between human curiosity and cosmic mystery. We are beings capable of discovering phenomena that operate on scales far removed from our everyday experience, yet we can somehow comprehend and even harness these effects for practical purposes. This suggests something profound about the nature of intelligence itself. Consciousness has evolved to the point where it can contemplate the quantum foundations of its own existence. The same neural networks that allow you to experience thoughts and emotions operate according to quantum mechanical principles, creating a beautiful recursive loop where quantum systems study quantum systems. The implications ripple outward into every domain of human knowledge. Philosophers have long debated the nature of identity, asking what makes you uniquely you from moment to moment. Quantum entanglement offers a new perspective on this ancient question, suggesting that identity itself might be relational rather than absolute, emerging from the patterns of correlation that connect your constituent particles to the broader web of cosmic interactions. Artists throughout history have intuited something about the interconnected nature of reality, creating works that seem to capture truths about universal connection and cosmic harmony. Now, quantum mechanics provides a scientific framework for understanding these insights, revealing that the aesthetic sense of unity and interconnection reflects something deep about the structure of reality itself. Musicians speak of resonance and harmony, of instruments finding sympathetic vibrations that create beauty through coordination. The quantum world operates on similar principles, with particles finding correlations that transcend space and time, creating patterns of connection that maintain their coherence despite the forces that would destroy them. Writers and poets have always known that language creates connections between minds, allowing thoughts and feelings to leap across the gaps between separate consciousnesses. Quantum entanglement suggests that this kind of correlation might be more fundamental than we ever imagined, woven into the very fabric of physical reality rather than being merely a human invention. The practical applications continue to unfold with breathtaking speed. Quantum technologies that seemed like pure science fiction just decades ago are now moving from research laboratories into commercial applications. The first quantum computers, though still limited in their capabilities, have already demonstrated their ability to solve certain problems faster than any classical machine could manage. These early quantum devices are like the room sized computers of the 1940s, impressive in their pioneering achievements, but still far from reaching their full potential. Yet they represent the first tentative steps toward a technological revolution that could transform computation, communication, and our understanding of information itself. The quantum internet is beginning to take shape as well, with entangled particles distributed through fiber optic networks connecting quantum processors across continents. These networks will enable new forms of distributed computation where problems can be solved collaboratively by quantum machines working in perfect coordination despite being separated by vast distances. Imagine weather simulations that harness quantum processors around the globe, each contributing its computational power, while quantum entanglement ensures that the overall calculation remains coherent. Picture medical research projects where quantum computers in different countries share quantum states directly, exploring molecular interactions with unprecedented precision and speed. The security implications are equally profound. Quantum cryptography promises communication channels that are fundamentally secure, protected not by mathematical complexity, but by the basic laws of physics themselves. Any attempt to intercept quantum encrypted messages necessarily disturbs the quantum states being used for communication, automatically alerting the legitimate parties to the presence of an eavesdropper. This quantum guaranteed security could revolutionize everything from banking and commerce to diplomatic communications and personal privacy. In a world where classical encryption methods face constant threats from advancing computational power, quantum cryptography offers the promise of truly unbreakable codes based on the deepest principles of reality. But perhaps the most intriguing applications lie in the realm of quantum sensing and measurement. Devices that exploit quantum entanglement can detect changes in gravitational fields, magnetic fields, and other physical quantities, with sensitivity approaching the fundamental limits imposed by quantum mechanics itself. These quantum sensors might detect gravitational waves from the earliest moments of the universe, revealing the cosmic symphony that has been playing since the beginning of time. They might peer into living cells without disturbing their delicate biological processes, watching quantum effects in photosynthesis and other vital functions. They might even detect the subtle quantum signatures of consciousness itself, finally bridging the gap between physics and the mystery of subjective experience. Medical applications of quantum technology are particularly promising. Quantum magnetic resonance imaging might provide detailed pictures of the brain while it thinks, revealing the neural correlates of consciousness with exquisite clarity. Early detection of diseases might become possible by monitoring the quantum coherence of biological systems, catching disorders before they manifest as visible symptoms. The pharmaceutical industry is already exploring how quantum computers might revolutionize drug discovery by simulating molecular interactions with perfect accuracy. Rather than relying on approximations that classical computers must use, quantum processors could model the quantum mechanical behavior of drugs and disease targets directly, potentially accelerating the development of new medicines by decades. Climate science could benefit enormously from quantum computation as well. The Earth's atmosphere is fundamentally a quantum mechanical system where countless molecular interactions determine weather patterns and climate trends. Quantum computers might provide the computational power needed to create truly accurate climate models, helping humanity understand and respond to environmental challenges with unprecedented precision. Yet, for all these technological marvels, the deepest impact of quantum entanglement might be philosophical rather than practical. This phenomenon has forced us to confront fundamental questions about the nature of reality, causality, and our place in the cosmic order. It has revealed a universe far more subtle and interconnected than our classical intuitions suggested. The journey from Einstein's skeptical objection to today's quantum technologies illustrates the remarkable power of scientific inquiry to transform philosophical puzzles into practical tools. What began as an abstract debate about the completeness of quantum theory has evolved into engineering challenges and commercial opportunities that are reshaping our technological landscape. This transformation reminds us that science is not just about accumulating facts, but about developing new ways of seeing and understanding the world around us. Quantum entanglement has given us fresh eyes for examining reality, revealing patterns and connections that were always there but remained invisible until we learned how to look. The story continues to unfold as new experiments push the boundaries of what we can observe and control. Scientists are creating entangled states with ever more particles, maintaining quantum correlations over ever greater distances, and developing ever more sophisticated applications of these mysterious connections. Each advance brings fresh surprises and new questions. The quantum world seems inexhaustibly rich in phenomena that challenge our understanding while opening new possibilities for technology and insight. We are still in the early stages of learning to think quantum mechanically, to see the world through the lens of correlation and connection rather than separation and independence. As our gentle exploration draws toward its peaceful conclusion, we find ourselves changed by the encounter with these quantum mysteries. Like particles that cannot return to their original state after interaction, our understanding of reality has been permanently altered by this journey through the looking glass of quantum mechanics. The universe revealed through the study of entanglement is not a collection of separate objects, but a single interconnected whole, temporarily expressing itself through patterns we call particles, people, and planets. In this view, consciousness itself becomes a cosmic phenomenon, the universe developing the capacity to observe and understand its own quantum nature through minds like yours. Tonight, as you prepare to release conscious awareness and drift into the quantum realm of dreams, carry with you the knowledge that you are part of something magnificent and mysterious. You are quantum mechanics made manifest, a temporary arrangement of fields and correlations that has achieved the remarkable feat of wondering about its own existence. The boundaries between self and cosmos, observer and observed, knower and known, become beautifully blurred in the quantum perspective. You are not an isolated individual contemplating an external universe, but rather the universe contemplating itself through the miracle of conscious awareness, connected to every particle that has ever existed through the invisible threads of quantum correlation. Sweet dreams, fellow quantum traveler, in this cosmos where mystery and meaning dance together in patterns of infinite beauty and complexity, where the simple act of curious wonder reveals that reality is far stranger and more wonderful than we ever dared imagine, and where consciousness itself might be the universe's most sophisticated expression of the quantum entanglement that binds all things together in the eternal dance of existence, becoming aware of itself through minds like yours, drifting gently into the quantum realm of sleep and dreams. The morning will come, as mornings do, and with it the return of classical consciousness from its quantum sojourn through the realm of dreams. But something will have shifted during those hours of neural reorganization, some subtle recalibration of how you perceive the spaces between things, the connections that persist despite apparent separation. You'll find yourself noticing correlations where before you saw only coincidence. The way sunlight seems to dance with shadow, each photon carrying within its quantum state the memory of every interaction since its birth in the nuclear furnace of our star. The electromagnetic radiation warming your face has traveled 93 million miles, yet it arrives carrying correlations established in the sun's core, quantum information encoded in patterns of energy that somehow bridge the vast emptiness of space. Even your morning coffee becomes a meditation on entanglement when you consider that the water molecules dancing in your cup have journeyed through countless cycles of evaporation and condensation, each H2O molecule maintaining quantum correlations with partners scattered across oceans and clouds. The caffeine that soon awakens your neural networks operates through quantum mechanical processes, electrons hopping between molecular orbitals in your brain cells, creating the cascade of awareness that transforms sleepy contemplation into alert consciousness. This heightened sensitivity to connection reveals itself in unexpected moments. You might find yourself pausing while walking through a forest, suddenly aware that every leaf rustling in the breeze is connected to every other through quantum field fluctuations that propagate at the speed of light. The trees themselves become quantum computers, processing information through photosynthesis, in ways that seem to violate classical thermodynamics, but make perfect sense when you understand that chlorophyll molecules use quantum superposition to find the most efficient pathways for energy transfer. Birds overhead navigate using quantum compasses in their cells, detecting Earth's magnetic field through entangled electron pairs that maintain their correlations despite the constant tumult of biological activity. Even the simple act of listening to their songs becomes profound when you realize that sound waves are collective quantum excitations, disturbances in fields that connect every molecule of air between the bird's throat and your eardrums. The transformation extends to human relationships as well. Conversations take on new depths when you recognize that communication itself is a quantum phenomenon, with meaning emerging from the correlations between neural patterns in different minds. The words traveling from speaker to listener carry quantum information encoded in pressure waves, electromagnetic fields, and the subtle dance of particles that makes all communication possible. Love, in particular, reveals its quantum nature through the mysterious synchronicities that lovers often report. Two minds that thinking the same thought simultaneously, reaching for the phone just as it rings with a call from the beloved, finishing each other's sentences in ways that seem to transcend ordinary explanation. While science cannot yet measure romantic entanglement directly, the phenomenon hints at connections that operate below the threshold of conscious awareness. The workplace becomes a laboratory for observing quantum effects in complex systems. Teams that achieve remarkable coordination despite minimal explicit communication might be tapping into quantum correlations between their neural networks. Creative collaborations, where ideas seem to emerge spontaneously from group interactions, could represent collective quantum processes, consciousness networks achieving coherence across multiple minds. Art galleries and concert halls transform into spaces where quantum aesthetics reveal themselves in new ways. Paintings that seem to shimmer with inner light might be exploiting quantum effects in pigment molecules, creating visual experiences that operate at the intersection of physics and perception. Musical performances become explorations of quantum harmony, with instruments creating acoustic correlations that resonate not just in the air, but in the quantum fields that underlie all matter. The digital devices that surround us take on new significance when understood as primitive quantum machines. Every smartphone contains billions of transistors operating according to quantum mechanical principles, electrons tunneling through barriers in patterns that would be impossible in classical physics. The screens displaying these words manipulate quantum states in semiconductor crystals, creating photons with precisely controlled properties that somehow translate into meaning in your visual cortex. Internet communications reveal their quantum foundations when you consider that information traveling through fiber optic cables consists of entangled photon streams, quantum states propagating at light speed through networks that span the globe. The website you're reading exists as patterns of quantum information distributed across servers worldwide, maintained through electromagnetic correlations that persist despite constant hardware changes and updates. Social media platforms become visible manifestations of quantum network effects, with ideas and emotions propagating through human networks in ways that mirror the correlations between entangled particles. Viral content spreads through quantum like mechanisms where observation changes the system being observed, each view and share creating new correlations in the vast web of human consciousness. The news itself takes on quantum characteristics in our interconnected world. Events happening on one continent instantly create correlations with responses on others, information propagating through networks at speeds that sometimes seem to transcend the classical limitations of cause and effect. Financial markets exhibit quantum like behavior where observation affects outcomes, and the mere act of measuring economic indicators changes the economic reality being measured. Weather patterns reveal their quantum nature through sensitivity to initial conditions that operates at the molecular level. The butterfly effect becomes literally quantum mechanical when you realize that tiny fluctuations in electromagnetic fields can cascade through atmospheric systems, creating correlations between events separated by vast distances and time scales. Urban environments pulse with quantum rhythms as millions of individual decisions create collective behaviors that emerge from the statistical mechanics of human interactions. Traffic flows, economic trends, cultural movements all exhibit properties that mirror quantum phenomena, with individual randomness giving rise to predictable collective patterns. The food you eat carries quantum information from its origins, molecules that have been shaped by quantum processes in soil, sunlight, and cellular metabolism. Each bite connects you to agricultural systems that depend on quantum effects in photosynthesis, nitrogen fixation, and countless other biological processes that operate at the intersection of chemistry and physics. Sleep research continues to reveal new connections between consciousness and quantum mechanics. The brain waves measured during different sleep stages might represent macroscopic quantum phenomena, neural networks achieving coherence across billions of cells through mechanisms we're only beginning to understand. Dreams themselves could be explorations of quantum superposition. Consciousness temporarily frees from the constraints of classical logic and causality. Memory formation and retrieval show quantum characteristics as well. The way forgotten experiences suddenly resurface through seemingly random associations might reflect quantum tunneling effects in neural networks. Information stored in quantum states that become accessible through specific patterns of brain activity. Learning itself appears to involve quantum processes as neural connections strengthen through mechanisms that depend on quantum mechanical effects at synapses. The moment of understanding, when disparate pieces of knowledge suddenly cohere into insight, might represent a kind of quantum phase transition in consciousness. Language evolution demonstrates quantum like properties as words and meanings propagate through cultural networks, changing through interactions that create new correlations between sound and significance. The way metaphors leap across conceptual boundaries mirrors quantum tunneling, meaning traveling through barriers that should be impermeable to classical information transfer. Educational systems are beginning to incorporate quantum literacy as a fundamental skill for navigating an increasingly interconnected world. Students learning about entanglement aren't just studying physics, but developing new ways of thinking about relationship, causality, and the nature of information itself. Medical practice is being transformed by quantum technologies that can detect disease signatures through quantum sensing techniques. The human body reveals itself as a quantum system where cellular processes depend on coherence effects that persist despite the warm, noisy environment of living tissue. Therapeutic applications of quantum principles are emerging in fields ranging from psychiatry to physical rehabilitation. Understanding the quantum nature of neural networks opens new possibilities for treating conditions that affect consciousness, memory, and emotional regulation. Environmental science benefits from quantum perspectives that reveal ecosystems as interconnected networks where local changes create global correlations through mechanisms that operate across multiple scales of space and time. Climate change itself becomes understandable as a quantum phenomenon where human activities create correlations with atmospheric systems that persist for decades or centuries. Conservation efforts increasingly recognize that protecting biodiversity means preserving quantum information networks that have evolved over millions of years. Each species extinction represents the loss of unique quantum processes that cannot be recreated once they disappear. The night sky takes on new meaning when viewed through quantum eyes. Every star represents a quantum fusion reactor, creating the elements that make consciousness possible. The light reaching Earth carries quantum information that has traveled for years or centuries, maintaining correlations established in stellar atmospheres across the vast emptiness of space. Astronomy itself is being revolutionized by quantum technologies that can detect gravitational waves, analyze stellar spectra with unprecedented precision, and peer into the cosmic microwave background to study the quantum fluctuations that gave rise to galaxies and stars. Space exploration increasingly depends on quantum navigation systems and communication networks that maintain correlations across interplanetary distances. Future missions to Mars and beyond will rely on quantum technologies for everything from propulsion to life support systems. The search for extraterrestrial intelligence has taken on quantum dimensions as scientists consider whether alien civilizations might communicate through quantum channels that operate below the threshold of classical detection. The universe itself might be alive with quantum conversations we're only beginning to learn how to hear. Philosophy has been permanently altered by quantum mechanics, with traditional concepts of determinism, locality, and objectivity requiring fundamental revision. The questions that occupied ancient thinkers about the nature of reality have been given new urgency by discoveries that reveal the universe to be far stranger than anyone imagined. Religious and spiritual traditions find unexpected resonance with quantum principles that suggest fundamental interconnectedness and the participatory role of consciousness in creating reality. While quantum mechanics doesn't prove any particular spiritual belief, it does reveal a universe that operates according to principles that mystics have long intuited. The future stretches ahead, filled with possibilities that would have seemed like pure fantasy just decades ago. Quantum computers will solve problems that are impossible for classical machines. Quantum communication networks will enable unprecedented forms of human collaboration. Quantum sensors will reveal hidden aspects of reality that remain invisible to current instruments. But perhaps the most profound transformation lies not in any particular technology, but in the shift of perspective that quantum entanglement has brought to human consciousness. We are learning to see ourselves not as isolated individuals, but as interconnected aspects of a single quantum reality, temporary patterns in the cosmic dance of correlation and connection. The gentle wonder of it all settles around you like a soft blanket as the day continues its quiet revolution. Somewhere in the universe tonight, particles that were born together in the heart of a distant star are still maintaining their mysterious connection, still proving that reality is far more beautiful and strange than our everyday experience suggests. You carry this knowledge with you now, this understanding that beneath the surface of ordinary experience lies a realm where the impossible becomes routine, where connection transcends separation, and where consciousness itself might be the universe's most elegant expression of quantum entanglement. Rest well in this quantum cosmos, fellow traveler, where mystery and meaning interweave in patterns of infinite complexity and beauty, where every moment brings new discoveries about the interconnected nature of existence, and where the simple act of wondering about our place in the universe reveals that we are not separate observers, but integral participants in the grand quantum symphony of reality, becoming aware of itself through minds like yours. The profound implications of quantum entanglement extend into realms that challenge our most fundamental assumptions about the nature of existence itself. As we settle deeper into this contemplation, there's something almost mystical about how the mathematics of correlation seems to whisper secrets about the very fabric of being, secrets that our ancestors might have glimpsed through intuition but could never quite articulate. Consider the extraordinary fact that every measurement we make, every observation we conduct, participates in the ongoing creation of reality rather than simply revealing what was already there. This isn't philosophical speculation, but experimental fact, confirmed through countless tests that show the universe genuinely exists in states of possibility until the moment of observation collapses those possibilities into definite outcomes. The implications ripple through every aspect of human experience, like gentle waves, disturbing the surface of a perfectly still pond. When you reach for a book on a shelf, the quantum fields that make up your hand interact with those that constitute the book in ways that create new correlations, new entanglements that will persist long after you've forgotten the simple act of selection. These interactions accumulate throughout your life, creating an ever expanding web of quantum relationships that connect you to every object you've touched, every person you've encountered, every breath of air that has passed through your lungs. You are not moving through a static world, but participating in its continuous creation, your consciousness playing an active role in determining which of countless possibilities becomes actual experience. The laboratory experiments that revealed these truths represent some of humanity's most elegant detective work. Scientists have learned to ask nature very specific questions using instruments of extraordinary precision, and nature's answers have consistently challenged our most basic intuitions about how reality should behave. The correlations persist across any distance. The measurements remain perfectly coordinated. The quantum dance continues with mathematical precision that seems almost choreographed. Yet what makes these discoveries so compelling isn't just their technical achievement, but the way they illuminate the relationship between knowledge and mystery. The more precisely we measure quantum phenomena, the more we discover about the fundamental limits of measurement itself. The more we understand about entanglement, the more we appreciate how much remains unknown about the nature of consciousness and its role in the quantum realm. This dance between knowledge and mystery extends into the practical applications that are beginning to transform our technological landscape. Quantum computers exploit superposition to explore multiple solutions simultaneously, like having countless researchers working in parallel dimensions until the correct answer emerges from the quantum mist. These machines represent a fundamental shift in how we think about computation itself. The quantum internet that's taking shape will enable forms of communication that seem to border on telepathy, with information transmitted through quantum states that cannot be intercepted without detection. Security becomes guaranteed not by mathematical complexity, but by the basic laws of physics themselves, creating communication channels that are fundamentally private. Medical applications promise to revolutionize how we understand and treat the human body as a quantum system. Imaging techniques that exploit entanglement might reveal the neural correlates of consciousness with unprecedented clarity, finally bridging the gap between the objective world of physics and the subjective realm of experience. The philosophical implications grow more profound as we consider what quantum entanglement reveals about the nature of identity itself. If the particles that make up your body are constantly being replaced through metabolic processes, what maintains the continuity of your sense of self? Perhaps identity emerges not from the persistence of particular particles, but from the patterns of quantum correlation that bind them together into the coherent system you call yourself. This perspective transforms our understanding of memory as well. Rather than being stored in specific locations, like files in a computer, memories might exist as patterns of quantum correlation distributed throughout neural networks. The act of remembering could involve recreating these quantum states, bringing past moments into present awareness through the mysterious alchemy of consciousness. The boundary between self and world becomes beautifully fluid when viewed through the lens of quantum mechanics. Every interaction creates new correlations that persist beyond the moment of contact. You are constantly becoming entangled with your environment, exchanging quantum information with everything around you in ways that blur the traditional boundaries between observer and observed. This interconnectedness extends across scales from the microscopic to the cosmic. The atoms in your body were forged in stellar furnaces billions of years ago, carrying within their quantum states the memory of those ancient nuclear processes. You are literally made of star stuff, quantum fields temporarily organized into the pattern of conscious awareness, connected through invisible threads to the far reaches of space and time. The night sky takes on new meaning when understood as a vast network of quantum correlations. Every photon reaching your eyes from distant stars carries information about conditions that existed years or centuries ago, maintaining quantum relationships across the emptiness of space. The universe reveals itself as a single interconnected system where local events create global correlations through mechanisms that transcend our ordinary understanding of cause and effect. Art and music find new resonance in the quantum realm. When a painter captures light on canvas, she's working with electromagnetic radiation that exhibits quantum properties, creating visual experiences that operate at the intersection of physics and perception. Musicians explore acoustic correlations that propagate through quantum fields, generating patterns of sound that somehow translate into emotion and meaning in the listener's consciousness. Language itself becomes a quantum phenomenon when we consider how meaning emerges from the correlations between sound and significance. Words travel from speaker to listener as disturbances in quantum fields, carrying information that creates new patterns of neural activity in the receiving mind. Communication becomes a kind of entanglement between consciousness, where ideas propagate across the space between separate minds through the subtle dance of particles and waves. The emergence of artificial intelligence adds new layers to these mysteries. As machines become capable of processing quantum information, they might develop forms of awareness that operate according to principles we're only beginning to understand. The boundary between biological and artificial consciousness could become as fluid as the boundary between classical and quantum reality. Future technologies might enable direct sharing of conscious states through quantum networks, creating new forms of empathy and understanding that transcend the limitations of language and symbol. Imagine experiencing another person's memories directly, sharing their emotions through quantum correlations between neural networks, or collaborating on creative projects where individual minds merge temporarily into collective consciousness. These possibilities raise profound questions about the nature of individual identity in an interconnected quantum universe. If consciousness can be shared through entanglement, what happens to our sense of being separate selves? Perhaps the feeling of isolation that characterizes so much human experience reflects our limited understanding of the quantum connections that already bind us together. The therapeutic implications are equally intriguing. Understanding consciousness as a quantum phenomenon might lead to new treatments for mental illness that work by restoring quantum coherence to disrupted neural networks. Depression and anxiety could be understood as disorders of quantum correlation, treatable through techniques that enhance the entanglement between different brain regions. Pain itself might be reconceptualized as a disruption of quantum information processing, with relief coming through methods that restore proper correlations between sensory networks and consciousness centers. The placebo effect could be explained as a quantum phenomenon where expectation creates real changes in neural quantum states. Sleep and dreaming reveal their quantum nature when we consider that consciousness must somehow maintain continuity across states that seem fundamentally different. The transition from waking awareness to dream consciousness might involve shifts in quantum coherence patterns that allow the brain to explore possibilities that are normally suppressed by the constraints of classical logic. The content of dreams themselves could reflect quantum superposition states where multiple narrative possibilities exist simultaneously until the moment of awakening collapses them into remembered fragments. The strange logic of dreams, where impossible events seem perfectly natural, might reflect the fluid nature of quantum reality, where ordinary rules of cause and effect don't apply. Memory consolidation during sleep becomes a quantum process where neural networks reorganize their correlations, strengthening some connections while allowing others to fade. The mysterious way that sleep enhances learning and creativity might involve quantum tunneling effects that allow information to bridge gaps between previously unconnected neural networks. Even the simple act of falling asleep transforms into a quantum meditation when understood as the gradual relaxation of the correlations that maintain waking consciousness. As awareness fades, the quantum coherence that binds billions of neurons into unified experience shifts into different patterns, allowing new forms of information processing that remain largely mysterious to our current understanding. The journey through these quantum landscapes reveals consciousness itself to be one of the universe's most remarkable achievements. Somehow, through billions of years of evolution, matter has organized itself into patterns capable of contemplating their own existence. Quantum fields have learned to observe quantum fields, creating recursive loops of awareness that seem to bootstrap themselves into ever greater complexity and understanding. This recursive nature of consciousness, studying consciousness through quantum mechanics, creates beautiful paradoxes that hint at even deeper mysteries. We are quantum systems investigating quantum systems, using quantum processes in our brains to understand quantum processes in the world around us. The observer and the observed become aspects of a single quantum phenomenon, temporary patterns in the cosmic dance of correlation and connection. The mathematical equations that describe entanglement point toward truths that transcend their formal structure. Behind the symbols and calculations lies something that feels almost alive, a universe that seems designed to create connection, to resist separation, to maintain relationships across any distance and through any obstacle. The cosmos reveals itself as fundamentally relational, where being emerges from the patterns of correlation between quantum fields. As our gentle exploration draws toward its peaceful conclusion, we find ourselves transformed by the encounter with these mysteries. Like particles that cannot return to their original state after interaction, our understanding of reality has been permanently altered by this journey through the quantum realm. We carry with us now a deeper appreciation for the profound interconnectedness that underlies all existence. The spooky action at a distance that once puzzled Einstein has revealed itself to be one of nature's most beautiful principles, a cosmic love song where particles maintain eternal connections across infinite distances. Through studying these connections, we've discovered that we ourselves are part of the song, conscious notes in the grand symphony of quantum correlation that plays throughout the universe. Tonight, as you prepare to release conscious awareness and drift into the quantum realm of dreams, remember that you are not falling asleep alone. You are part of a vast interconnected system where every quantum interaction creates new correlations, new relationships, new possibilities for connection and understanding. The boundaries between self and cosmos dissolve into the gentle recognition that separation itself might be the grandest illusion of all. Sweet dreams, fellow quantum traveler, in this cosmos where mystery and meaning dance together in patterns of infinite beauty and complexity, where consciousness and cosmos intertwine in the eternal quantum waltz of existence, becoming aware of itself through the miracle of minds like yours, drifting gently into the quantum realm of sleep, where new correlations await discovery in the morning light. The story of quantum entanglement is still being written in laboratories around the world tonight, where dedicated researchers continue to push the boundaries of what we thought possible about the nature of reality itself. In Vienna, a team adjusts their laser alignment for the thousandth time, preparing to send entangled photons across record distances. In Tokyo, scientists work with atomic clocks so precise they could detect the gravitational time dilation caused by raising them just a few centimeters. Each experiment adds another brushstroke to the portrait of a universe far stranger and more beautiful than we ever dared imagine. What makes these ongoing discoveries so remarkable isn't just their technical precision, but the way they continue to surprise us even after decades of quantum research. Every time physicists think they understand the limits of entanglement, nature reveals new depths to explore new ways that particles can maintain their mysterious connections across the vast emptiness of space. The implications continue to ripple outward into domains we never expected. Quantum biology has revealed that living systems exploit entanglement for everything from photosynthesis to possibly even consciousness itself. The warm, wet environment of biological tissue should destroy delicate quantum states within nanoseconds. Yet somehow life has learned to harness these effects for its most essential processes. Consider the robin navigating by quantum compass, or the plant converting sunlight with quantum efficiency that surpasses our best solar panels. Evolution has been conducting quantum experiments for billions of years, creating solutions that our most advanced laboratories are only beginning to understand and replicate. The future stretches ahead filled with possibilities that would have seemed like pure magic. To our ancestors, quantum computers will solve problems currently beyond our imagination. Quantum communication networks will connect minds across continents with perfect security. Quantum sensors will detect phenomena that remain invisible to our current instruments. But perhaps the most profound transformation lies not in any particular technology, but in the shift of perspective that quantum entanglement has brought to human consciousness. We are learning to see ourselves not as isolated individuals struggling alone in an indifferent universe, but as interconnected aspects of a single quantum reality, temporary patterns in the cosmic dance of correlation and connection. This understanding transforms everything from how we approach scientific research to how we think about love, friendship, and the bonds that connect us to one another and to the natural world around us. The boundaries between self and other observer and observed begin to dissolve into a more fluid understanding of existence itself. As quantum technologies mature from laboratory curiosities to everyday tools, we can expect even more startling applications. Quantum medicine might heal by restoring coherence to disrupted biological systems. Quantum psychology might understand consciousness as patterns of entanglement across neural networks. Quantum ecology might reveal ecosystems as vast quantum computers processing information through networks of living correlation. The philosophical implications grow deeper with each passing year, challenging our most basic assumptions about the nature of time-space, causality, and consciousness itself. We stand at the threshold of a transformation in human understanding comparable to the discoveries of Copernicus, Darwin, or Einstein. Yet for all these grand possibilities, the most beautiful aspect of quantum entanglement might simply be what it reveals about the present moment. Right now, as you listen to these words, you are participating in quantum processes that connect you to the farthest reaches of the cosmos. Every breath creates new correlations. Every heartbeat maintains quantum rhythms that have persisted for billions of years. The photons carrying this information to your eyes began their journey in the quantum dance of electrons. In distant power plants, traveled through networks of fiber optic cables where they maintained entangled states across thousands of miles, and now create patterns of neural activity in your visual cortex. Through quantum processes, we are only beginning to understand you are not merely observing the universe, you are the universe observing itself through the miracle of conscious awareness. Quantum fields temporarily organized into the extraordinary pattern of a mind capable of contemplating its own quantum nature. The observer and the observed revealed as aspects of a single underlying reality. The gentle wonder of it all settles around you like a soft embrace as you prepare to drift into the quantum realm of sleep, knowing that even in dreams, your consciousness will continue to explore the mysterious connections that bind all things together in the eternal dance of existence. Somewhere in the universe, tonight, particles that shared a common origin billions of years ago are still maintaining their quantum connection, still proving that separation is an illusion and that at the deepest level, everything remains forever entangled in the beautiful mystery we call reality. Sweet dreams, dear traveler, in this quantum cosmos where every moment brings new revelations about the interconnected nature of existence, where consciousness and cosmos dance together in patterns of infinite complexity and beauty, and where the simple act of wondering about our place in the universe reveals that we are not separate observers, but integral participants in the grand quantum symphony of reality. Becoming aware of itself through minds like yours, as you close your eyes tonight, remember that you carry within your very atoms the history of stars, the memory of cosmic evolution, and the promise of discoveries yet to come. You are quantum entanglement, made manifest walking proof that the universe has learned to contemplate its own deepest mysteries through the extraordinary emergence of conscious awareness. As we reach the gentle conclusion of our quantum odyssey, perhaps the most beautiful realization is that this journey never truly ends. Every night as you close your eyes, every morning as consciousness returns, you're participating in the same mysterious dance that connects particles across cosmic distances. The boundary between the scientific and the sublime becomes wonderfully blurred when we recognize that we ourselves are living expressions of the very phenomena we've been exploring. Think about the remarkable fact that the neurons firing in your brain right now, as you process these final thoughts, are creating quantum correlations that will ripple outward into the universe long after this moment has passed. Every synaptic spark, every flash of understanding adds new threads to the vast web of entanglement that connects all conscious beings across space and time. The questions we've explored tonight don't have tidy answers wrapped in neat conclusions. Instead, they open doorways to even deeper mysteries that will occupy curious minds for generations to come. What is consciousness? What is reality? What does it mean to exist as aware beings in a quantum universe that seems designed for connection rather than separation? These aren't just academic puzzles, they're invitations to see the world with fresh eyes, to notice the correlations that surround us, to appreciate the profound interconnectedness that quantum mechanics has revealed lurking beneath the surface of everyday experience. You'll never look at a sunset quite the same way, knowing that each photon carries quantum information from nuclear reactions 93 million miles away. The children being born tonight will grow up in a world where quantum technologies are as commonplace as smartphones are today. They'll navigate quantum computers, take for granted communication channels secured by the laws of physics itself, and perhaps most remarkably, they'll think quantum mechanically from an early age, seeing connection where we once saw separation, understanding correlation as naturally as we understand cause and effect. For them, the spooky action at a distance that puzzled Einstein will be as intuitive as video calls across continents are to us. The impossible made routine, the mysterious transformed into the marvelous through the patient work of scientists who refused to accept that nature's deepest secrets were beyond human comprehension. As you drift toward sleep tonight, carry with you this gentle understanding that you are part of something magnificent and mysterious, that the universe has spent 14 billion years learning how to contemplate its own existence through minds like yours, that consciousness itself might be the cosmos developing the capacity for wonder, curiosity, and love. The quantum realm awaits your dreams, where the usual rules of logic and locality give way to possibilities limited only by the imagination of a universe that seems determined to surprise us at every turn, where particles dance across impossible distances, maintaining their eternal connections in the cosmic ballet of existence. Rest well, knowing that tomorrow will bring new discoveries, new mysteries, new reasons to marvel at the extraordinary fact that we exist at all in a reality far stranger and more wonderful than our ancestors ever dared imagine, where the simple act of looking at the world with curious wonder reveals secrets that transform our understanding of everything. Sweet dreams, fellow quantum traveler, in this interconnected cosmos where mystery and meaning dance together in patterns of infinite beauty and complexity, where every moment of conscious awareness represents a small miracle in the grand quantum symphony of reality becoming aware of itself through the miracle of minds like yours, drifting gently into sleep with the knowledge that you are forever entangled with the magnificent mystery of existence itself. The spooky action at a distance continues its eternal dance, and you, dear listener, are part of that dance now and always in this quantum universe where connection transcends distance, where wonder transcends understanding, and where consciousness transcends the boundaries we once thought divided us from the cosmos we call home. Until we meet again in another gentle exploration of science's most beautiful mysteries, sleep well and dream of particles dancing across the stars, connected by invisible threads of correlation that prove once and for all that in this quantum universe we are never truly alone.